Hello everybody, in this lecture we will be solving 1987 IMO problem number 3. Here's a view of this problem. We are given real numbers x sub 1, x sub 2, x sub n satisfying this following condition. We would like to show that for every given k greater than or equal to 2, there exists integers a sub 1 through a sub n not all equal to 0 such that the a sub i's are bounded by this condition and they also satisfy this weird inequality actually. Okay, to begin with, because our x sub i's are real numbers and they satisfy this condition and where their squares add up to equal to 1, let's assume that all the x sub i's up to x sub m are all non-negative, so these are all greater than or equal to 0. In this range though, we will just assume that they are all less than 0, or strictly I should say. Well, what happens if all the x sub i's are greater than or equal to 0? Well, in that case, we would say that m is equal to n. If all of them are negative, all the x sub i's, then in that case, we would say m is simply 0. So, after this convention, so now let's have a look at the left-hand side of the inequality that we would like to show. For the time being, let's consider the following sum. So, inspired from the left-hand side, I would like to focus on this sum here. X sub 2 and so on, c sub n, x sub n, and for the time being let's not worry about the negative numbers, so integers. So let's assume that all the ci's, even though they can take negative values, let's say that where the ci's are all coming from this range 1 and so on all the way to k minus 1. I would like to see under what conditions the values of s will be minimized and maximized. I claim that the s will be minimized when we pick c, the sequence c sub 1 through c sub n, in the following sense, because the first m terms of this x sub I sequence is all positive. I first need to set all of them as 0 for the first m terms. And then afterwards, I will have to set them at the maximum attainable level, which is k minus 1 each. So for terms m plus 1 through n, we would have set them. And as a result, s will attain its minimum value of, so plugging in all these numbers, so 0 times x1 would be 0 and so on. So all we would be left with would be k minus 1 times x, so let me write that down, k minus 1 times x sub m plus 1 all the way to k minus 1 times x sub n. Now notice that all the x sub m's, from x sub m plus 1 all the way to x sub n, these are all negative, and multiplying with positive coefficients, we really have a negative expression, which is minimized apparently. Okay, in a similar way, if I pick my coefficients such that the first m terms are k minus 1 and the remaining terms are simply 0. So basically I'm just flipping the coefficients here. In that case, s will be maximized and the maximum value will attain k minus 1, x sub 1 all the way to k minus 1 x sub m. So in this occasion, I would like to have a look at the distance between s max and s min. So that would imply that this distance is equal to, well, obviously we can subtract them. So it would be k minus 1 parentheses, we can factor out the k minus 1, and we would have x sub 1 plus all the way to x sub m, and then a minus another k minus 1, this time from x sub m plus 1 all the way to x sub n. Okay, and finally I can combine those things out, so I can the factor out the x k minus 1. So when we have x sub 1 minus, well, x sub 1 plus all the way to x sub n, each of these are apparently positive numbers, And then I have also these negative numbers here, x sub n plus 1 all the way to x sub n. However, each one will come with a negative sign here. As a result, I can rewrite this whole thing as x sub 1 plus all the way to x sub n in absolute values. Now at this moment, I would like to utilize the Cauchy-Schwarz inequality. So by Cauchy-Schwarz inequality, notice that a1 square all the way to an square times b1 square all the way to b sub n square is greater than or equal to a sub 1 b sub 1 all the way to a sub n b sub n squared. Now here let's replace the a sub i's with the x sub i's and the b sub i's with 1's. So what we have in the final case would be something like this: x sub 1 squared plus all the way to x sub n squared, 1 squared plus all the way to 1 squared. And apparently by Cauchy-Schwarz, this whole thing is greater than or equal to x sub 1 times 1 plus x sub 2 times 1 all the way to x sub n times 1 squared. Now let me have some more space here. So we have, as a result, well, also knowing that, remember that this thing is equal to 1, and this thing we have n terms here, so that would be equal to n here. So therefore, and finally, if we take the square root of both sides, what we come up with is that is basically going to be the desired result. Before I proceed though, I should clarify something here. On the right hand side, I should have put here absolute values here, because that's what it is, right? The square root of x sub 1 square is actually the absolute value of x sub 1 and so on. So what we have on the left hand side after we take the square root is that square root of n is greater than or equal to this nice sum, which is somehow interesting for us, that we will make use of. And now if we apply, now if we plug this into our original expression, we just realize that, so therefore, following up with this equation here, we can say that S max minus S min, the range of values that this S function, this sum product sum function can take. So we still have the k minus 1 times x sub 1 plus all this sum here, x sub n, but we have just recently proved that this thing is, and the left and the second term is less than or equal to square root n, so therefore we would have k minus 1 times square root of n. So therefore all values of s will fall into this interval, right? So therefore s for any generic values, they will fall into this range from S min to S max. I would like to go ahead and partition this range from S min all the way to S max into n equal subintervals, where let me write this down here in writing. So partition the interval S min all the way to S max into n equals to 2 to the n minus 1 subintervals, and each one will have a length equal to the range we had here earlier that we calculated here, this range divided by n, right? So because we are trying to create this many subintervals, so so therefore each of the intervals partition into it, each with length as we described earlier, S max minus S min after the partition, equal partition, is divided by n. Recall how we defined n. Obviously, because we have the way we originally defined the set of coefficients c sub 1 all the way to c sub n, now we can confidently say that we have these n tuples, and for each c sub I it can take where let me remind you again that each c sub I was coming from this set here, pulled from this set. As a result, each one can take k different values. So in total, we have k to the n values for s. But now notice that each subinterval of ours would have a length of s max over s min over n. And here, if you substitute the n itself, you will get this range where 2 to the n minus 1. So what that means is each subinterval will have to, so we'll end up having at least 2 distinct n tuples going into the same subinterval. Let the 2 n tuples that go into the same subinterval be c sub 1 prime all the way to c sub n prime, and c sub 1 double prime all the way to c sub n double prime, and they both go into the same subinterval, producing s values and these summation values that will have a difference no more than this bound here. So therefore, so implying that s prime, let's call the first one, would be simply c sub I prime of x sub I over all I, and s double prime is equal to summation c sub I double prime x sub I over all I. Now if we look at the difference, as I mentioned here, so this difference will be s double prime minus, or the other way around, it wouldn't matter actually, so would be in the range in this following range, so s max minus s min all divided by n, or you can just write it as 2 to the n minus 1 if you will. So let's just for now call it n. And finally consider the following ai. So let's define, a sub i's, remember the a sub i's in the problem set, in the following way. So this will be equal to c sub I double prime minus c sub I prime for all I equals from 1 all the way to n, and we obtain a sequence of integers, and not all will be equal to 0 because by definition c prime and c double prime, they are different vectors or sequences of n tuples, and as a result we would get this very handsome result. So this difference s double prime minus s prime is actually by definition equal to a sub 1 x sub 1 plus all the way to a sub n x sub n. And notice that we have just found that this thing is less than or equal to s max minus the minimum sum possible, all divided by n. And now wait, what we had earlier, if I'm not mistaken, was that s max minus s min, we were able to bound it in this range, so we can definitely replace those with what we have in that range again. So s max minus s min is k minus 1 times root n. So we have this thing is hold on, I think this is a typo here. I really wanted to say k to the n minus 1 here, sorry for that. But anyhow, so going back, so we have k to the n minus 1 here, and for the numerator, we observing this result here, earlier result, we have k minus 1 multiplied by square root of n. So we have found the magical integers a sub 1 all the way to a sub n, which satisfy somehow, they pull themselves from this interval, so any integer values in this range, and basically satisfy the property that this function here, the left hand side is definitely less than or equal to the right hand side of the problem. So we are done. Hope to see you in our next video.